Yeah. So let's recall. So we consider the following probability distributions at n. So maybe I put Zn of G exponential of minus n raised of okay, so let me not put G here. First of all, trace of B of H, where B of H is something like 1/2 H squared. And then you can have plus, I don't know, G over 4, H4 plus some higher order terms. And of course, we had this, yes, Zn is equal to the total integral over Hn of this guy, e to the minus n raised of, yes, E of H. So in particular, if we just have this, we say we have a quartic model. In that case, we don't bother with higher order terms. And many examples is really covered by this quartic case in physics, for example. Okay, so all the things that we discussed for GUE can be asked for this. So now the problem is find large and limit probability distribution. Okay, now just to get a bit of feeling for these things, it's always a good idea to start with n equal to 1, actually. Although we want to let n go to infinity, but let's start at n equal to 1, see what kind of object we have. So, and I'm honestly changing the question now. So I just want to introduce some technique for a different problem, but it's going to be eventually useful. So let's look at n equal to 1. Then in that case, we have the following thing to consider. 1 over ZG. Yeah, so exponential of minus n is 1 anyhow, 1/2 x squared plus g minus g. So I'm going to use minus this time over 4 x4. Okay. Okay, dx. So this is a probability distribution on the line on R. I mean, of course, for G equal to 0, right? We have a standard normal distribution. This reduces to a standard normal, right? So this is the standard normal. That's for G equal to 0. But for G positive, this integral is still convergent, even convergent better, because this is going to 0 much faster now, even. So for G positive, this is a probability distribution, and we want to get an idea of the shape of this probability distribution. How does it look like, right? So because in this, so for G equal to 0, we have a standard normal. This is G equal to 0. Now for G positive, it's going to be some distribution. I mean, the mean is still 0, but well, how does it look like? I don't know. I mean, there's no easy what am I trying to say in this case? I mean, the probability distribution is there. I mean, this is the probability distribution. So this is, so there's no problem with the distribution. This is the distribution. It's just, we see it. What we want to know its moments, basically. I mean, you can graph this curve. I mean, that's not difficult to graph it. I mean, it's just basically like this. It really goes to 0 much faster. It's kind of sharper. It's not Gaussian. It's a sharper version. But what we are interested in to know is the moments of this. So I should kind of, yeah, clear myself here what I'm trying to say. Yeah. So the problem is not find. Okay, so this was the problem for the original problem, but now the problem now is find moments of this distribution. So by this distribution, I mean this. So basically, so i.e. the following numbers. So we have Mn is equal to 1 over Z of G, right? Integral Xn, right? Integral Xn. And then, well, e to the minus 1/2 x2 negative G over 4 x4, sorry, negative G over 4 x4 dx. This is what we want to know, what these numbers are, the moments of this probability distribution. Okay. All right. So one thing which is very easy to observe in this case is that odd moments are all 0 again, right? By symmetry argument. So first of all, M0 is equal to 1 because this is the total mass. And M2K plus 1 is equal to 0. That's by symmetry. Odd function integrals, so this is over R. And what we don't know is what is M2K, basically. For K equal to 1, 2, 3, so all higher even moments are unknown to us, except in one case where G is equal to 0, right? Except when G equal to 0. So do you remember the even moments of the Gaussian? At G equal to 0, we have the Gaussian, right? So do you remember the moments of the Gaussian? In other words, the following thing. M2K 0 is 1 over Z0 integral x2k exponential of minus 1/2 x squared dx. Do you remember what that number was?
I think it was 2k minus 1 double factorial, the product of the odd numbers.
Exactly. That's 2k minus 1 double factorial. So products of all odd numbers, exactly. Yes. And this 2k minus 1 double factorial is exactly also the number of pairings of a set with 2k elements, right? This is equal to number of pairings of the set 1, 2, 2k. So if you put this 2k points, and then you take all possible pairings, and that's we already counted this. It's 2k minus 1 double factorial. Okay, so these numbers are some functions of g, strange functions of g, which at g equal to 0 are these values, but we don't know what those values are for g positive. So we want to know. At least we want to get a handle of those on those numbers, because this integral is kind of, it has been calculated, and I want you to look it up, because I think in terms of some strange maybe gamma functions or something, but it's I mean, mathematical now computes these things quite easily, but I want what really matters is the method I want to introduce. Okay, cool. So now there are two ideas that we are going to use in this project. So I will even introduce them in this context, although, I mean, this is not what we intend to do in general, but still it's a good idea to introduce them. Two ideas. One is related to something called Schwinger-Dyson equations. So this Schwinger-Dyson equations comes under zillions of other names, really. So they are also called Migdal equations. Migdal, Marchenko, some Russian mathematicians, physicists, sorry. Equations also comes under the name of loop equations. Come under the name of loop equations, and then I don't know, sometimes it's called word identities in physics. So there are many, many names. I want you to know that they are really essentially the same idea that I'm going to introduce in this very simple context. Okay, so what is that we want to introduce? What is that idea we want to introduce? Well, look, I mean, if I just differentiate under the integral sign, I'm going to get 0, right? So the idea is the following. 1 over zg integral over r ddx of xn e to the minus 1/2 x squared minus g over 4 x4, right? Dx is equal to 0. This is true for all n. Equal to 0, 1. Right? I mean, because this function, even with xn in front, is rapidly decreasing at infinity, because this is exponential decay at infinity, this part, right? And so when we differentiate like this, you have to evaluate at minus infinity, plus infinity, or near that, by fundamental theorem of calculus. But those are, they approach to 0, so the difference is going to be 0. So this is 0 no matter what. Okay, but now let's see what we get if we differentiate, actually. If we differentiate, we just use Leibniz rule, right? We can just differentiate this times that and so on. So let's see what we get. So we get 1 over, so this zg I can cancel from both sides, because this is, so I get the integral over r. So this is n, xn minus 1, right? n xn minus 1 e to the minus 1/2 x2 minus g over 4 x4 dx. Okay, so n xn minus 1 times this, and then I just say plus xn. Okay, so let me not write it here. Plus then xn. And then if we multiply, we get minus, if we differentiate this, we get negative x. And this one, we get gx cubed. Gx cubed, right? Times e to the, okay, so I'm getting minus 1/2 x squared minus g over 4 x4 dx. So this we get this whole thing equal to 0, right? Okay. So I can multiply, I can divide this by z of g if needed. That's okay. So let me keep it here. I don't have to, because I need them. Okay. So then this implies that so n minus 1, you've got m sub n minus 1. So that's a bit unfortunate. I'm using m and n in the same thing. So, oh, that's okay. I'm going to change n very soon. So I've got n minus 1 plus, or rather minus, that term is mn plus 1. And then this term is minus g times n plus 3 x, so mn plus 3, basically I'm getting equal to 0, right? Okay. So this is true for at least n bigger than equal to 1. You agree with this? So it looks like we get a recursion between these values for n minus 1, n plus 1, and n plus 3. Okay. So now we can actually now assume, so let then n be equal to 2k plus 1, and then k is bigger than equal to 0. Okay, so let's assume n is 2k plus 1, k bigger than 0. Then I've got here 2k plus 1, right? This is m2k, because the even ones are the only ones that we care about, right? I've got m2k here, minus m. Here is 2k plus 2, minus m2k plus 2, a negative g, m2k plus 4 equal to 0. So this is the thing. So this is a 3-term recursion. Okay, so now, so we know that m0, of course, is equal to 1, right? We know m0 is equal to 1. So if I have then m2, if we know m2, right, then we can compute m4. from this, because still k equal to 0, we get M4. And then, okay, so then we get M4. So k equal to 1, we have M2 and M4, then we get M6 and M8 and M10 and all this, right? So this leads to M6, leads to M8. So, yeah, I mean, this is a three-term linear recursion, actually. It's an easy recursion in this case, linear recursion, right? So this is solvable, basically, provided we know M2, right? So what is M2 now? M2 is equal to 1 over ZG integral, I hope I don't go, so x2 exponential of minus 1/2 x2 minus g over 4 x4 dx. Yeah. But this M2 is hard to compute. I mean, in this case, again, it's not very hard to compute. I mean, numerically, of course, nothing, no problem. But even there are some closed formulas in terms of gamma function or Bessel function values or something. You can, I suppose, okay, I don't know. Okay, so this is still not so bad, but it's not the point. The point is the method. M2, so if we know M2, so we are supposing that M2 is very hard to compute. So this recursion becomes rather useless if we don't know what M2 is. So that's the thing. We have to know what is M2. So for M2, I'm going to introduce another idea. And the two of them together will give us a computationally nice method to compute actually basically all of them. Okay, so before we move on, are there any questions? Yeah. So it's always a good idea to check the case g equal to 0. So what do we obtain for g equal to 0? So for g equal to 0, we get this very interesting relation that m to k plus 2 is equal to k plus 1 m to k. And that's kind of nice because then you can continue equal to 2k plus 1 times 2k minus 1 times m to k minus 2, right? Because this third term vanishes. So this is equal to all the way, you continue, then eventually you get this is equal to, then you do get this is equal to, finally we get m to k plus 2 equal to 2k plus 1 double factorial, because it boils down to m2 of 0, right? Because this is m2 of g, but m2 of 0 is just the variance of the standard normal, which is 1. And this is the formula that we just recalled at the beginning, that this is the case. So if you want, this is also alternative way of getting moments of standard normal distribution. There are zillions of ways to do that, but this is another way. But this is good because it kind of checks, at least in one case, that we are not on very bad ground. I mean, we are on rather solid ground here, because for g equal to 0, we get the correct result. So, but the point is g positive. that we want to know what's going on. So I keep this recursion like that. Now, how to compute M2 of G? So the second idea now, it's related to something called hamburger, I should say, maybe, moment problem. Oh, I think he was a German mathematician before, in early 20th century. Hamburger, maybe, I think he was from, well, he's at least, I don't know, Hamburger moment problem. So what is this? What is this problem? It's a very interesting idea and is a very interesting question. The question is the following. So let okay, so let mu x dx be a general probability distribution on R. So we have a very general probability distribution on the real line. So it's positive and total mass is 1. It's a general probability distribution. Okay. This is mu of x. And so let's look at the moments, Mn equal to the nth moment. Moment of mu, which is by definition equal to the moment of mu is equal to integral xn d mu of x. Okay, so I don't know. So mu of x dx, let me put it this over R. Now, okay, so maybe I keep this here still, I don't know. Okay, I can just write this in this corner without erasing it. 2k plus 1 m2k minus m2k plus 2 minus g m2k plus 4 is equal to 0. Okay, so that's what we need. Okay. So now, so the question is now, this what relations Mn has. So the following term is true. The sequence Mn n equal to 0 up to infinity is such that the matrix so this matrix now is an infinite by infinite matrix. We just write. So the first row is M0, M1, M2, M3. You put all the moments in the first row. Okay, you put all the moments in the first row, and then you shift to the left, you get the second row. So the second row is going to be M1, M2, M3, M4, and so on. And the next row, again, you shift, you get M2, M3, M4, and so on. And then you get M3, M4, and so on. This matrix is positive semi-definite. Is positive semi-definite. Positive semi-definite means that any corner of this you cut, starting from here, and then 2 by 2, 3 by 3, 4 by 4, is a positive semi-definite matrix. And for this means that it's a symmetric matrix. Of course, it is symmetric. And all these determinants basically are positive. So this means all determinants delta n's is equal to determinant of, I mean, this top left corner is bigger than or equal to 0. I mean, determinant equal to 0 is okay, but cannot be negative. It means that the eigenvalues of the symmetric matrices are all non-negative. This is the theorem in one direction. So yeah, I don't know. I think maybe Hamburger discovered this himself. Although Hamburger proved something, the very difficult part of the theorem, which I don't write now. But this is the first observation that this sequence of numbers, moments, satisfy this condition. Satisfy this condition. So there are infinite number of equations, inequalities the moments have to satisfy. Who would believe that? So you have just some probability distribution, mu x. I mean, yeah, take any function, has to be non-negative and total mass has to be 1. And then you form these numbers, you get a matrix which is is a positive semi-definite matrix. It's really incredible observation that this is true. Okay, then let's see the proof. We still have time. So the proof of this positive semi-definiteness proof we need some fact from linear algebra. Need a linear algebra fact. This linear algebra fact, I think perhaps, if not in the very first year course of linear algebra, definitely it's proved to you in the second course of linear algebra, second year, third year linear algebra courses. Let's see. So the fact is the following, that if I have it, so I'm going to write it in general, Aij for any symmetric matrix. So I'm assuming it's symmetric matrix equal to A, which is Aij. So it's very general thing. You just take a n by n symmetric matrix. In this case, actually, these are real. I mean, but the theorem is also true for Hermitian matrices, but that's okay. For any symmetric n by n matrix A, this matrix is positive semi-definite. A is positive semi-definite. If and only if the following thing is true: the inner product of AX and X which is basically X transpose AX, is bigger than or equal to 0 for all vectors X belonging to Rn. In other words, this sort of quadratic function that you form using your matrix, which we also used when we discussed Gaussian integrals in the first lecture. We used similar things. This quadratic form actually never takes negative values. It's always at least 0. You cannot go to, I mean, yeah, cannot go below 0. This is if and only if. Okay. So, this linear algebra fact, I can prove it, but I will give to you as an exercise for now, so that you can enjoy proving it and brushing up maybe a little bit of linear algebra. But what I want to do now, I want to use this condition of semi-definiteness. I mean, semi-positive, semi-definite, semi-positive, definite. I mean, semi-positive. It's semi-positive. Okay, to prove this hamburger theorem. Okay. So back to our probability distribution. So what do we know? We know that the following integral has to be non-negative. So I've got a0 plus a1x. Yeah, plus a2x2 plus an minus 1, xn minus 1, right? I put squared d mu of x is bigger than or equal to 0, right? Of course, this much we know. I mean, if you take any real numbers, is a0, a1, a2, an minus 1, if you pick n minus 1 real numbers, and then you form this function, which is a square of a polynomial, it's non-negative function. So we compute its integral against this measure probability mu, it has to be non-negative, right? Has to be non-negative. Now, what is this? What is this thing? So if you think about it, you notice that actually this is left-hand side. This is equal to actually the following thing: a0, a1, an minus 1 times this matrix m0, m1, m2, and n minus 1. And then here I've got, I don't know how many I pushed. So if I push m0, I get to m1 here. So I don't know, what should I put here? Mn minus 1 maybe? And then Mn minus 2. And then I've got a0, a1, an minus 1. Let's check this in some special case.
Shouldn't we have mn on the bottom row, second column?
Yeah, I mean, here I'm sure, okay, you think it should be mn, right? So
No, not the first one. The first one is okay as mn minus 1, but the second entry on that row.
here you mean?
Yes,
The last row, exactly.
yes.
So the last row, yeah, mn minus 1, then of course this moves on, it moves forward. Yes, absolutely, mn. Yeah, thank you. Yeah. Excellent. Yeah. Yes, so let's check this for example 2. I mean, if you put a0 plus a1x squared d mu of x, now you want to integrate this. What is that? If you just square this, you're going to get a0 plus a, okay, so you get a0 squared plus 2a0 a1 x plus a1 squared x2 d mu of x, right? Yeah, a1 x squared. Yeah, so if you compute one by one, you're going to get a0 squared, and integral of 1 is what we call m0. We know m0 is 1, but let's put it plus 2 a0 a1 and 1 plus a1 squared, that's m2, because integral of x2 d mu of x is m2, right? Okay, and what is that? That's exactly a0 a1. Oh, okay, I have to put it like the other way around. That's exactly a0 a1, and then m0 m1, and then m1 m2, and then this is a0 a1. But we know that this is non-negative because of properties of measure, probability distributions. So this is bigger than or equal to 0. So this is bigger than. And if you move on, you can do it for 3 terms, 4 terms, and so on. You convince yourself that this statement is actually correct. And that's it. Using this linear algebra lemma, we are done. It's really an amazing observation. I mean, I don't know. I mean, this is not something that, yeah, this is really like magic. It's incredible that this is true, actually. But it is true. I mean, once we are told that this is true, we can check it. Yeah, but just to think about it is kind of. As an aside, I should say that, so this observation in this part, in this side is not, okay, we can verify it. If we are told, we can verify. But what Hamburger really proved was the converse. He showed that given any sequence of numbers, m0, which is a 1, and m1, m2, m3, so on, that satisfies this positivity, that satisfies infinite number of conditions, provided that sequence has some, is not growing too fast, then there is a probability distribution on the line whose moments are these numbers. And that's really a remarkable result, which I still don't know how to prove. I tried to prove it myself, I couldn't. So if you can see the proof or you have an idea of the proof, just let me know. Just I will ask you to give me just a very small hint. I don't want to see the complete one. I just want to get a very, very, very small hint so that I can cheat a little bit, but not too much. Okay, so now, so let me write this, the other side, and then we move on. Okay, so conversely, Hamburger proved for any sequence, yeah, m0, m1, m2 of real numbers, such that m0 is equal to 1, and the main P. So by the way, that matrix that I wrote is called Hankel matrix of this sequence. And the Hankel matrix So this is M0, M1, M2, and then I've got M1, M2, M3, and then M2, M3 is positive semi-definite. Then, provided MNs don't grow too fast. Okay, now the reason I'm formatting right is that I don't remember what is the condition, but there's a condition that the idea is that they should not growing very fast. I mean, if they grow very fast, we cannot. I mean, there is something which I don't remember exact condition, but you can find it in Wikipedia, for example, such that don't grow fast. Then there exists a probability distribution mu x dx such that mn is equal to integral x and mu x dx. So these are kind of inverse problems because we are given the sequence of moments and we want to want to see if there is a actually distribution, probability distribution, whose moments are these ones. So, I mean, it looks like the relation between moments and probability distributions is almost 1-to-1. I mean, by this thing. So, and it's really a great result. I mean, so these moments are like Taylor expansion or Taylor coefficients of some analytic functions. Of course, but it's in the case of analytic function, it's very easy because these are just those coefficients in front of xn. But these moments are just these strange integrals. I mean, much more complicated relation. But nevertheless, there is this issue here, which is anyhow. So that's what we are going to use in bootstrap technique. I mean, this is kind of this circle of ideas is very, very important. Yeah. So now what we want to use, we want to actually now use this positivity to restrict the choices for G. I'm sorry, the choices for M2 now, okay? So then use this positivity, or non-negativity, I should say, this semi-positivity to restrict the choices, I mean, the range of, I would say, M2 of G. Because all that matters for us is just this M2 of G, right? M2, because the rest are completely obtained by the. So we have some determinants. So, for example, the next one, M0, M1, M1, M2. I mean, this has to be bigger than or equal to 0, but we know that M1 is 0, so this is basically nothing but M0, M2 bigger than or equal to 0. So this is nothing because we know that it has to be true because M2 is the variance. So it has to be true. So this is useless. Let's go to the next one. M0, M1, M2, and then we've got M1, M2, M3, and then we have got M2, M3, M4, right? Okay, so, but we have to use this information. So M1 is 0, here is 0, M3 is also, so this determinant of this, okay, I should say determinant of this guy. This is determinant of this guy is bigger than or equal to 0. Okay, so this is still 0. This is 0. So this is M2 appearing here, and here is M4. But we can just know that M4 so GM4, we can solve this, is equal to, if K is equal to 0, is equal to M0, which is 1. Okay, so it, yes, minus M2, right? So M4 is equal to 1 over G M0 minus M2. So we put M4 here, which is 1 over G. M0, which is 1. Okay, so I put here 1, and then this is 1 minus M2, right? Okay, so we got this condition. Okay, now the task is to compute this determinant. So this is your weekend exercise. Please compute this determinant and see what kind of condition you get for M2. You should get, hopefully you will get something for like M2 less than equal to something, because we know it's bigger than equal to 0. So you restrict your range of M2. And the next thing is we go 4 by 4. I mean, in principle, we have to go infinite by infinite, but infinite number of times, but that's not needed. If you go far enough, hopefully you will bound M2 good enough. I mean, so right now, actually, this problem is a toy problem. It's not the actual problem. It's something that I and Nathan basically cooked up. I came up with the idea and I checked with him and he thinks it's a good idea. So I think we can just, I mean, maybe if we get something like in between, so if you can sandwich M2 between narrow enough bands, then you have got a good idea of what M2 is. And then you can also then, and the idea is to find maybe the first 10 moments or the first 13 moments, something like that. This is computer work, of course. But for now, I would suggest you look at this non-negativity of this determinant and the next one over the weekend and see what you see. I want you to see if this is conclusive, is getting anywhere or not. Because I mean, it depends on these inequalities. If you can sandwich between the two, that would be very good. But if we cannot sandwich them, it's not very useful. I mean, yeah, somehow. Okay, it looks like so. This is like a open problem, really. I don't know the answer, and it's not written anywhere. So this is new. So you can. Is a fun exercise to get involved. So when we go to random matrices, we'll play a similar game. We have two things. These equations, recursions, which we get using Schwinger-Dyson equations, and positivity, which we get from this Hamburger observation, Hamburger's theorem. And then the two together, we'll try to solve some of these models. This is called bootstrap in random matrix theory. It's called bootstrap because it looks like you're computing the integral without without even computing the integral. Just use positivity. So there's some constraints. It's kind of it's like you're pulling yourself yourself. So pulling up by pulling your shoestrings. It's bootstrapping, something like that. I think it's okay for now. I mean, unless you have questions. Yeah, and if you come across, if you happen to think about the proof of this converse problem that Hamburger solved, let me know. I'm very interested to know. I tried to. I don't know how to prove it. Okay. Okay. So if there are no questions, then maybe then we meet again on Monday, or perhaps I think Nathan can take over at one stage, but we'll see. We'll see soon. And if this, another thing is, okay, so this is now getting towards our project. That's pretty good. I'm glad we ran these sessions before the start. But I don't want to just stop here. I want you to also know a little more general random matrix theory issues, which would be useful anyhow, independent of project, because these are not. So sometimes I tell you things that are not directly related to the project, but still it's good to know. I mean, because random matrix theory is a fascinating subject. It's good to know those issues, yeah. And think about it at least, yeah. All right, thank you very much. And if you have any questions, as usual, please send me a message or email. I'll be happy to get back to you. Have a great weekend.
Have a nice day.
Yeah,
See you
thank
soon.
you. See you. Bye.
Bye.
Bye-bye.